Thank you, Eric, for the very nice introduction. So as Eric mentioned, I do too many things, which means I do nothing. So I'll give the corporate introduction to Scikit-learn, which is the very big picture. And Tom, who's been working much more on the code than myself, will give the technical part of the talk. Tom is one of the many people who make Scikit-learn great every day. So my goal is to give some perspective on Scikit-learn, and to give perspective on the historical dynamics and on the future prospects. And let me start with the development dynamics and just a bit of history. If we go back, many, many years, our original vision was to democratize what's known as machine learning, which really is really a branch of applied math. So it's really, so these days we talk a lot about AI and data science, all these things, but we were a bunch of computer science researchers, and we wanted to put those algorithms that you read in papers in the hand of everybody. And by everybody back then, we were mostly thinking of people like us, not people outside of the lab. But we still thought it was important to make it accessible, make it easy to use, and easy to understand. I guess that's part of the vocation of teaching when you're a researcher. We also wanted to make it a tool for something like production. By this, I mean that we wanted things that were reliable, and hence we avoided oversimplifications. Some things cannot be boiled down to a simple solution, in which case we didn't try, because such a simple solution would fail. And we also targeted very high quality software engineering. So there's a bit of this trade-off between democratizing machine learning, but keeping something that is production ready rather than a toy. And finally, last but not least, we cared a lot about open source. We wanted it to be open in many different ways, including open community, beyond the walls of our lab. So that was almost 10 years ago. And in 2009, version 01 was released by our team, a bunch of researchers at INRIA. And what I did when I prepared this talk is I went through the release notes of all these many versions, and I could kind of see the history of the project. It was quite interesting. So 2 years after the first release, we had the first international sprint at a machine learning conference. And this was really a great moment, because this is when I felt that the community was picking up. There were people whom we really didn't know who came and who worked really hard on this project together with us. And it was just a fantastic feeling. And many years later, we won the prize at the Open Data Science Conference for best tool, and I think I'm quite proud of this. And so if I went, if I go through the history of things that we added, we started by maybe the most, we basically started by the most boring machine learning models, including support vector machines. And the fun thing is we didn't even actually implement support vector machines. The only thing that we did was we did a better binding to libsvm in Python than the ones that were already available. That was already a strong start. And then we added, simple things, linear models. Oops, I translated these slides from French and not well. So linear models, and we kept adding new things. And here is something interesting is happening. Random forests. Random forests is definitely a technique that we in our lab back then were not interested in. We were not looking at these things. And it appears in Scikit-learn because it's an important technique and because somebody else is contributing it. And that's really the value of having an open project, is your project goes beyond the bounds of what you think is relevant. And so things keep coming up, and this is in French, so half of the audience is not understanding, but it doesn't really matter. We got sparse data, we got parallel computing, now we're focusing on distributed computing and categorical data. So it's really interesting to see how features grow. And then we can look at the growth in terms of users. And this is the analysis of the monthly website traffic in terms of unique sessions. And so you can really see that it's going up quite a lot. These days we're getting more than 500,000 of returning users on the website. And because the documentation, the most easily available documentation, is on the website. That gives us hope that these are people who are actually using the software. Because of software is free and embedded in many distributions, we don't really know how many users we have. And the downloads are not a reliable count because bots download software to run continuous integration. So that's the best guesstimate that we have, so a bit more than 500,000. So we think it's a pretty large impact. We have more than 500,000 of active users. If we look at the distribution of what OS these people use, well, half of them use Windows. How many people use Windows in the room? Well, it looks like a third. What I take from this half of the people using Windows is that we've kind of crept out of the horrible geese, the people who have ponytails. So that's good, because we're hopefully reaching out to normal people. That's good. I won't get a haircut. So we have, these days we have something like 12,000 academic citations, which is pretty big. I wish I had another paper that had that much. And if we look at our users, approximately 1/3 of them are in academia and 2/3 in industry. And this is something we're really happy about, because we want, as researchers, to spur research, but we also want to spur innovation and technical growth. So that's something we really like. Now, if we look at the growth of the community, what I'm showing you here is the number of monthly active contributors, okay? So, and they're not the same every month. It really varies. So what you can see is that it grew, and at some point it kind of stabilized, and you've got peaks, and those peaks are sprints. It kind of stabilized, and we approximately have 25 active contributors per month, which is quite a lot, because as I say, these people vary. So it's 25 people who push in a feature that's quite often a reasonably major one, because we've got strong merge criterion. I think it's a pretty active project. Something though is quite interesting is the way it levels off. And that's not surprising, because when a project reaches a certain complexity, and these days scikit-learn is a complex project, when it reaches a certain complexity, it just becomes really hard to work in it. And it's really hard to work in scikit-learn these days. It kind of, segues from the previous talk. I think we're pretty good at keeping bounds on our technical depth, but there's just only a limited amount of things that you can do to limit complexity. So it's not surprising, but it's a bit disappointing. But it's just not surprising. And now if we look at how the activity of these contributors is distributed, so this is, contributor number by first being the person who has the most amount of activity. And if we look at the amount of activity distributed by contributor number, what we find is we have typically a 1/f curve. So a few people are extremely active, and we have many occasional contributors. Now this curve, of course, is a gross simplification, because it's counting commits, which is a terrible number. And also, maybe we should split it by years, because what you'll find is that different people are active at different moments. But nevertheless, it's a fairly unsurprising curve. It's a fairly classic curve that you've got this kind of behavior in open source projects. And this could be just a bug fix or a typo or something like this. It's still very useful. But where I'm getting at is that these people are pretty important. I did a list of the 20 people who contributed most in the last scikit-learn release, and I wasn't on it. I was number 21st, so I'm not part of these people anymore. So what we're seeing here is that we have in scikit-learn, even though it's an open source community-driven project, what we have in scikit-learn is a professional core. People who act as professionals. And professional, I don't mean, by this I don't mean whether they're paid or not, whether they're officially on their LinkedIn page software developers. I mean people who behave like they're committed to the project and keep going back at it and spending a lot of time on it every month. And a bunch of these people are paid to work on the project. I listed here people who were paid more than half time to work on the project in 2018, and I hope I didn't forget anybody. but we have a bunch of people at INRIA. So INRIA is the French national research in computer science and applied math. So we have a bunch of people paid on different funds. We have people at Columbia, and we have somebody at Sydney University. So these are really very important people. And you can see where I'm going is that, well, we need money to pay these people. So I'm not here to ask you money, that's fine. But we realized that for the sustainability of the project, we needed to switch a bit the way we were working. And basically, we realized over the year that public money was depending on public money was a liability for us. Because public money is something that comes and goes. I can tell you this, it's my job to find public money. And so we set up a foundation to depend on sponsoring. So sponsoring comes and goes also, but there's a bunch of people who were interested in joining us. And so the difficult exercise here is to mix community-driven development with industrial interests. And we think, so it's a difficult exercise because there are dangers that the community loses interest in the project. And so the way you fix this is you engage the community in the decision of the people who are paid by the sponsors, and also and by doing this, basically, you put those people at the service of the community. So they do things like taking the garbage out. Refactoring. And then you get a mixed governance between the community and the sponsors. So we did this. And the goal really is to keep the energy and the confidence of the community, but also to take strategic recommendations from the industry because it's interesting. So we've got a bunch of people who joined us. Honestly, I was surprised and excited to see the interaction with those people. So we've got people like consulting people, the BCG Gamma. We've got I don't know if you know this company, Microsoft. They do some things. We've got banks. We have hardware producers. We've got a startup that does data science studio on top of scikit-learn. And what I can tell you is that the discussions with these people have been extremely fruitful. Basically, working with them, we have the feeling that we're working in the interest of the project. Enhancing the interests of the community. And it's really been technical discussions. It's like, what should be our priorities? How do we, mitigate technical depth? So that's really the right level of discussions. So it leads me to a few comments on where we might want to go. And really, there's a core question is, how do we position ourselves with regard to the ecosystem? There's a vast ecosystem. We've got companies, projects that have major backing from companies. TensorFlow has Google behind them. They've got a 100-people team. They're just moving so fast on every aspect, marketing and everything. We still think that we are relevant and that we're going to continue being relevant. And one of the reasons is that we're doing an interesting trade-off between the different extremes. We're not the most performant, but we're reasonably performant. We're very versatile. And that's quite useful. We're able to move in production. And so we're just going to try to stick to this trade-off, but expand in all directions to keep this trade-off of something that's versatile, but able to go in production. So really, the new ambitions are going to be, and these were established between the community and the sponsors, are going to be things like focusing on improving interpretability and model confidence, on data integration, and Tom will be talking a lot about this, on scaling up with distributed computing, and on more frequent and better versions. And with this, I'd like to thank everybody who worked with us and give the floor to Tom.
Okay, so I'm gonna talk a bit more about technical stuff, and I'm gonna focus on transformers. So if people know about Google's transformers, it's nothing about Google Transformer, which is a neural network. This is an API word that we use to talk about a class of estimator which transforms the data. The basic API is just like standard scaler, for example, which just scale your data just before using it in an other estimator. And here is the API. You just call fit maybe to compute what is the scale of your data, and then you can transform either your train set or your test set. But I don't advise you to use this API. Well, you can, obviously, but there is a much better API, which is using the pipeline. Because with the pipeline, you just specify that you want to do a standard scaler, and then the classifier you want to use, maybe SGD classifier. And then it's very clean, and you can use this object model just as if it was the SGD classifier. You can use it exactly the same, so you can completely forget that you have specified to use a standard scaler. So this is a great way to code, because you have a clear overview of your pipeline. It's very readable. You are assured not to mess with the cross-validation, because if you do it by hand, you have a lot of chance that you will get things wrong with the linking, the pipelining. You have also a very easy to use grid search over parameters, because you can use this just as a classical estimator in the grid search CV object. And you can also cache the intermediate results, so you don't have to recompute every time the scaling. You do it only once, and you can cache the results. So this is very nice. It's not new to scikit-learn. And you have already a lot of transformers in scikit-learn before the last version, the 0.20. So you have, for example, PCA to reduce your dimensionality, but you have also scalars, encoders. You can expand with polynomial features. You have a way to impute your data when you have missing data, and so on. So this is nothing new, but in the new version that was released a few months ago, we did a lot of work to try to improve the typical data science pipeline. So we introduced a lot of new transformers. So here is a short list. I'm going to go through most of them, and also improvements on existing transformers. So to start with simple improvement, we added a better imputation. So we deprecated the imputer, the existing imputer, to have it basically the same behavior. It's called simple imputer, just to differentiate with more advanced imputer that we plan to implement. But a major update of this imputer is that it now handles categorical data. And this is something that was a bit lacking in scikit-learn, especially for the typical data science data sets that people use with categorical data. So categorical data is a category which is a feature which is not numerical. So for example, it might be let's say the sex of a person, male or female or something else. It can be something which is non-numerical. So you have to encode it, and it's you can now pass it to the imputer also. There is also a new missing indicator, which add a new feature where the data is missing. So it can be also quite useful, because sometimes missing feature is itself informative. We added also categorical data in the one-hot encoder, and we added a new encoder to specify a new way to encode the categorical data. So for example, if you have a feature which says small, medium, large, maybe you want to encode this, but you can also say there is an ordering between small, medium, and large, and maybe I want to associate this with 1, 2, 3. So this is easily done with the new ordinal encoder. We also added the possibility to use missing values in these transformers, in these existing transformers, and we plan to do it with many more. And this was the very easy to explain, but there are more advanced transformers that I want to explain more in depth. So I will start with the column transformer. The column transformer is very useful when you want to have a different transformation, a different pipeline for different features. So let's say, for example, you have both continuous and categorical features. And you don't want to split them beforehand. You want everything to be inside your pipeline. So what we do here is for example, we specify here what are the columns. Here it's with the Panda-friendly API. We specify the columns which are numerical. So for example, the age of the person, the fare they've paid. It's from the very typical, classical Titanic dataset. And here there are some categorical features. So the sex, the passenger class. And once we have specified this, we specify a different pipeline for both of them. And we give this into the column transformer. So each pipeline will be applied in the corresponding columns. So here, let me go through very briefly through this pipeline. So for example, here, the numerical pipeline, we can think about just imputing the missing data with a median strategy and then scaling the data maybe. And for the categorical data, we want also to impute the missing data. So this was not possible before. And also to one-hot encode them. And it was possible before, but with a much more complicated way. And this is much cleaner, very readable, very easy to. It's basically a pipeline that you can plug for a lot of like basic datasets. Another great new transformer is the power transformer. So in the case where you have a data which is not Gaussian, normally distributed like a Gaussian, like for example, you have 6 examples here at the top of non-Gaussian distribution. And we implemented 2 very standard transforms, the Box-Cox and the Yeo-Johnson transforms, which transform the data to make them the more Gaussian possible. So I don't know exactly the details of the transforms themselves, but it's very useful because a lot of different estimators assume that you have some kind of Gaussian data. So for example, if you think about just a linear regression, it will not behave very well if your data is not Gaussian. It will work, but maybe if you apply this before, it will work much better. So this is something that we added also. Another great new tool is a K-bin discretizer. Let's say you have a data here and you want to discretize the space. And it's also a way to use, for example, linear models on nonlinear data. And we implemented 3 different strategies. The first one is just a uniform. And the idea is you split the space, the input space, into just bins. And on each of these bins, you will have a different feature encoding these bins. And then you can learn a model just on these bins. So it's a simplification of the space, but sometimes it's enough to learn something. You can think of 2 other strategies, very natural. The first one is with using a quantile, so to have something which follow the distribution of your data, and something based on k-means. And to show you an example, here I have 3 different data sets. The 2 first ones are non-linearly separable, so if I use a linear model, it will not work well. So the second and the third column, we try to use linear models. So it's a logistic regression and a linear SVM, and it doesn't work very well. The 2 last columns, we used non-linear classifiers. So it's gradient boosting and SVM, but non-linear SVM. and it works quite well. But maybe we would like to use a simpler model than the SVM, which can be, the nonlinear SVM can be a bit costly. And using the K-bin discretizer, you can have a discretization of the space to allow the linear classifier not to capture this nonlinear dataset. So it's really something very useful. It's obviously non-very scalable if you have many, many features. But on simple dataset, on small number of features, it can be extremely useful. And it works very well in practice. And I'm sorry, it doesn't show the picture, but the next transformer is called, it's not exactly a transformer, but it's a new meta estimator, which is called the transformed target regressor. And here the idea is not to transform the input data, but the output data. So if you do a regression, let's say you have a distribution of your target that is non-Gaussian. And here again, it will not work very well with the linear regression, but you can transform the data, maybe with a log, because if it follows roughly a log distribution, it will behave better. But you also want to transform back after you have predicted the target, and because if you want to compare in the original space some kind of metric, you want the transformer to go back. So here is just a wrapper around the linear regression, where you specify a function that will be applied to the target, and after the prediction, it will apply the inverse transform. So here, for example, there is a log for the function and the exponential for the inverse function. So this is the end of all the different estimators that we introduced. We introduced also a very nice documentation page. I really advise you to check it, because this is really something I wish I had when I was starting using scikit-learn, and I still learned a lot of it from it, even though I'm quite experienced in scikit-learn. So the idea is just a list of terms we use in machine learning, and more specifically in scikit-learn, to talk about the different API classes, the different names of parameters that are commonly used. And it's really something that clarify your mind. So I really advise you to check this. Yeah, sure. And last thing I want to highlight of the latest release is the JobLib backend system. So JobLib is a library that is independent of scikit-learn, but is developed jointly. And this is the library that is used to do all the parallel computing in scikit-learn. So if you use scikit-learn, you've probably used n jobs equals something, saying you want to have more than one core, and this is what is used in the background. And with the new backend JobLib system, you can actually change the backend, and actually the default backend has changed also to a backend called Loki, which does not break a lot of third-party threading. So it's maybe not an improvement for most of you, but if you had problem with JobLib before, it solves most of the problems. So you can check this also, and you can actually change the backend now with this JobLib release. You can change the backend, and for example, if you use multiple computers, if you use a cluster, you might want to use Dask and distributed to scale the use of scikit-learn. And with this new backend system, you can just add 2 lines in your code and switch to the new backend, which is developed by Dask distributed and which is compatible with JobLib. So now I would like to talk about something a bit different, which is not from the latest release. It's about nearest neighbors. It's something I've been doing recently on scikit-learn, and I'm going to be a bit fast about this, but I'll go you through. So what is nearest neighbors? The nearest neighbors is just a very non-parametric way to explore your data. So let's say you have a point, a new point. Can you classify it? You can do a model, but you can also say, what is the closest point? I want to take the class of the closest point. Or maybe the closest point is not very robust. Maybe I want to take the 2 closest points or n closest point. And then I can say, OK, I'm going to take the mean or of the class or the value I want to predict. And here is an example with 1 neighbor, 2 neighbors, 4 neighbors. And it's able to learn the structure of the data just saying, let's go back to the training data and look at the closest point. And in scikit-learn, it's used in a fair number of different estimators, so classifiers, regressors, but also maybe you know t-SNE to represent your data in 2D, or some clustering techniques like dbScan or spectral clustering. And how is it computed? So you can either compute it brute force, computing all the pairwise distances, but you can also use a tree, a KD tree or a ball tree, to have a better structure of your data and save time computing all the neighbors. But actually, this is what is implemented in scikit-learn. You have also other methods that are approximated. The idea is you don't get exactly the nearest neighbors, but you can some reasonable guess of what are the neighbors. And the idea of the algorithm is based on random projection. So the more projection you do, the better you have, the more correct you are, but the more time-consuming it is also. And there are very good implementation in a Python package by Spotify or by Facebook Research, Annoy and Faiz, but also NMSlib and many more. And maybe we would like to use them in scikit-learn. But currently, the API is not very friendly to do that. So if you compare the performances of all these libraries, horizontally you have the recall, which is if you are to the right, it means that you have perfectly the true nearest neighbors. And if you are on the left, it means that you have your guess of nearest neighbors is quite poor. And vertically, you have the number of queries you can do per second. And so the higher, the better. And you see here, the 2 red circles, it's scikit-learn. So we are perfect because we don't use approximated method, but we are very slow compared to the other one. So maybe we can work on this API to allow you to use these libraries. So I'm going to go very quick about this because time is running. But the idea is that the API is a bit of a mess. Basically, you have 2 different structures that are basically the same and which do not have the same API. You have a different way to call the nearest neighbors internally. So sometimes it's inheritance, sometimes it's creating an instance inside the class, sometimes it's calling a function which calls which creates the nearest neighbors class and then discard it. And so everything is a bit of a mess. And it's really something we call technical debt here. We cannot blame the people that originally created this because they didn't have the vision of scikit-learn in the beginning, and obviously scikit-learn was more friendly to contributors at the beginning, and nowadays it's much more difficult to contribute, and something like that would be much more difficult to add. But this is something very difficult now to fix. And so here is also stating that all the parameters of the nearest neighbors estimation need to be copied on every class, and this is also a problem. So I'm going to skip this. The challenges are to have a consistent API, avoiding copying all the parameters. Also, the real challenge is that it's difficult to change the code. We don't want to break anyone that is actually using these weird features that were not maybe intended in terms of clean API, but which are there today, so we don't want to break them. And also we want to use approximated nearest neighbors. So the idea of what I proposed is still under review, but is to use a transformer to compute the sparse graph of nearest neighbors, because essentially computing the nearest neighbors is just a preprocessing. It's just a way to transform your data, saying the original data doesn't matter. It's just the distance to the original data that matter. And so the first step was to make all classes that rely on nearest neighbors accept the precomputed sparse graph, and then to create two new transformers which compute the nearest neighbors. And here I have two different models, one which is built with a pipeline, using first the computation of the nearest neighbors, and then the actual estimator, here, which is here t-SNE. And the second model is just with the internal implementation of nearest neighbors, and they behave exactly the same. It's just that with this API, you can control much better. Because first, all the parameters are accessible in the transformer. You can use the caching properties of the pipeline that I told you before to not recompute the nearest neighbors if you want to check t-SNE with different parameters. And you can also use external libraries like Annoy. Here I coded a wrapper around Annoy to have the same API as our transformer, and it goes much faster with basically the same results. So this is still under review, but it's just to present you an example of how to improve scikit-learn. It's really difficult because the code is quite complex. You have technical depth, but going somewhere to have a very clean API and to be a kind of framework to be able to reuse other libraries such as approximated nearest neighbors. So thank you for your attention. All the slides are in this website, and you can also follow me on Twitter if you want.
Thank you, Tom, very much. Are there any questions? All right, I'm going to run quickly.
Hey, thanks for the presentation. Just about the caching facilities, the last time I used scikit-learn, there wasn't any. I wanted to know if you support any sorts of remote caching, like, for instance, caching on S3.
Sorry, I don't hear you very much.
Remote caching, sorry, for instance, using an S3 bucket as a cache, so that, for instance, a pipeline that started on one computer and that crashed can be restarted on another and still use the caching. I wondered if these facilities were implemented or if it was planned or anything.
I have no idea. Maybe Gael knows.
Are you asking about the caching of the pipeline on S3?
Yeah, from the examples I saw local caching, but
there's been work in joblib. So that caching is done via joblib. There's been work in joblib to support this. The problem is we personally don't run S3, so I have no idea whether it's reliable or not. So you should like hammer on it and tell us if it's reliable or not.
I meant not necessarily on S3, but any kind of distributed storage. Okay, well, now I no longer remember whether the PR is merged or not. Where at least there's a storage backend PR. I think it's merged. Yeah, it broke everything when we merged it. There's a storage backend PR that implemented the storage backend. So you can even implement your own storage backend to say where you want to store. Do it, hammer on it, tell us if it works. We're interested. Okay, thanks.
So the PR is March.
All right, we have time for one last quick question, and then you can, of course, go see Gael and Tom. All right, let's move. Thank you. Let's thank them again.
I just want to say that Tom won one of the best PhD thesis awards from the École Doctorale. So, and it's not for his work in scikit-learn.